what is the average value of a function? Average value of f. Really, it's best to typically think about examples where f is continuous, though I did mention that some discontinuous functions can be integrated over some interval from a to b. By definition, it's the integral of f divided by the length of the interval. Different kinds of symbols people use for it. Maybe f bar. Maybe if you know some statistics, you know that x bar represents the average or mean of data values. So f bar could represent the average or mean of a function. I think I also sometimes call it v, or maybe v bar, the average value of f. Again, it's assumed over some interval. This is a u here, and then an e. Again, take the integral and divide by b minus a, or if you prefer, take 1 over b minus a, 1 over the length of the interval, times the integral. In applications, the units for the average value of a function are the same as the units for the function itself. That should make some intuitive sense. So, for example, if f of x is, say, an f of t and represents your average velocity or average speed, this could be in, for example, meters per second or centimeters per second or miles per hour or whatever. And I'm using an x, but it still could represent time. Maybe x is in seconds. So the units of the integral is then you imagine that you're multiplying here, even though you're not. F of x times dx would be in meters per second times seconds, rate times time, giving you a distance if f of x is the speed, and a displacement or change in position if f of x is a velocity. But the units are the same either way. Seconds cancel, leaving you with meters for the units of the integral. The integral itself doesn't affect the units because it's like adding. 1 over b minus a has units of 1 over whatever the units of x are. A and b are numbers on the x-axis. They have the same units as x. So if x is in seconds, this would be in 1 over seconds. And the final units for the integral times 1 over b minus a would then be in meters per second. So it's like you go from meters per second times seconds to meters, but then in the end, you divide by seconds again, and so you are left with units of meters per second in the end, which again should make sense if f represents a speed or velocity whose units are meters per second. You would want the average value to have the same units because it's still supposed to be measuring the same kind of thing. So as far as computing average value, it's very easy. You just use this formula. So for example, what is the average value of f of x equals, say, x squared over the interval from, let's say, 0 to 3? Just use the formula. Go 1 over 3 minus 0 times the integral from 0 to 3 of x squared. Leave the 1/3 out in front. Do the integral with the fundamental theorem of calculus. Antiderivative of x squared is 1/3 x cubed. You evaluate that from 0 to 3. 1/3 times 1/3 is 1/9. 3 cubed minus 0 cubed is 27 minus 0. In the end, you get 27/9, or 3. How about that? Is it a coincidence that that number matches that number? Possibly. How should you interpret this, the meaning of this, graphically? The graph of x squared, as x goes from 0 to 3, looks about like this. When x is 3, 3 squared is 9. The output of the function is 9. The value of the integral itself is 27. That's the area under this graph, 27. Is that reasonable? If you drew a triangle, a right triangle like this, its area would be 1/2 base times height. Oh, did I make a mistake? Actually, the integral is not 27. It's 27 times 1/3, which is 9. 1/2 times 9 times 3 is 13.5. That would be the area of this triangle. The area of under the curve itself is this thing. 1/3 times 27. 27/3, which is 9. That's the area under the graph. But that's not the average value. The average value is 3. How to interpret that? Well, if you think about this equation up here in another way, if you multiply both sides of this equation by b minus a, you could also write that f bar, the average value of f times b minus a, equals the integral of f from a to b. And so what you're saying is that the average value times the length of the interval equals the integral. The integral is the area under the curve. Is that an area? Well, b minus a is the base of a rectangle I could draw. And f bar could be thought of as a height. We got a value of f bar here equal to 3. If I draw a triangle, or excuse me, a rectangle with base from 0 to 3 and height of 3, that rectangle is going to have the same area as the region under the curve. This area and this area are the same. That's the way to geometrically interpret the average value. Does it have any uses? Well, sometimes you're just interested in knowing what is the average value of a function. For example, you might want to know what the average rate of rainfall was in the past day. Okay, now it's sunny today. Well, imagine it was raining in the past day. Sometimes it's raining hard, sometimes it's raining lightly, a mist. The flow rate of rain into your rain gauge varies over time, but might be continually positive for some day. What's the average rate of rain? Right, that would be a relevant kind of thing to report to the weather service if you use your rain gauge to keep track of things. Not only how much rain, but how fast it come down. They might be interested in that kind of thing. Of course, if they know how much is in your rain gauge, they themselves could figure out the average rate of rain. Physically, if f of x, or say f of t is a velocity, and t is time, in finding the average velocity, what you're doing is you're saying, what's the average speed that I went from time 0 to time 3? It's 3. In other words, if I start at the same point and end at the same point, I can either travel with this velocity the entire time, which changes. I'm starting out slow and then I'm going faster and faster and faster. I'm accelerating. Or I could go this constant velocity the entire time, and I would still end at the same place at the same time. More significantly, perhaps, I'm always referring to multivariable calculus in this class. If you take multivariable calculus, there are things in that class called double integrals and triple integrals. I've hinted at this before. You don't do them, but there are even quadruple integrals, quintuple integrals, and hextuple integrals. Yikes. Hextuple integrals have 6 integral signs in one problem. I've never personally done a hextuple integral, by the way. The biggest one I've ever done is a triple integral, and that's what people sometimes do for the biggest kind of integral they do in multivariable calculus. So you got those kind of integrals. You also have things called line integrals and surface integrals that you may have heard your physics teacher talk about, with like Gauss's law for electricity and magnetism. Those are hard concepts. They're made easier to understand if you think about average values. I'm not going to go into the details about why. Maybe on Friday I will. Not today. you can understand those concepts more easily if you think about it in terms of average value. You can think about average value in those contexts as well. Okay, so it's a helpful tool for understanding. Let's apply not only these ideas, but also the ideas about Riemann sums and the fundamental theorem of calculus. Let's apply this now for a little bit of time to probability and statistics. In fact, I could even think about this same example. So the average value of this example, f of x equals x squared, that's what this graph is, over the interval from 0 to 3 was 3. If I multiply f of x by some constant, 2, 1/10, whatever I want, I would change the function, I would change the area, I would change the average value. Could I change the average value in such a way that the area under the graph of f is exactly 1? Sure. The area under the graph of f is exactly 9, as it stands. If I multiply f by 1/9, I'll get a function over the interval from 0 to 3 whose area under the graph will be 1 instead of 9. F of x equals 1/9 times x squared will have an area under it equal to 1 over the interval from 0 to 3. But let me do something a little funny. Let me write f of x as a piecewise function. I'm going to make it be 1/9 x squared if x is between 0 and 3. So that would again be this example that I was hinting at. That'll be a function whose integral from 0 to 3 will equal 1. I will redo the calculation over here. The integral of 1/9 x squared from 0 to 3 will be ultimately this, which ultimately equals 1. Because the length of the interval is 3, its average value would be 1/3. So you can relate this to average value if you like, though I'm now going to veer away from relating it to average value. What else will f of x equal? It's going to be 0 if x is less than 0 or x is bigger than 3. So it's a function whose graph between 0 and 3 looks like this. It's a parabola. Its value at 3, you can see is 1/9 times 3 squared is 1. That's actually just a coincidence that the value at the right endpoint equals the area under the curve. That's just a coincidence. And again, it's 0 otherwise. So it's got a jump discontinuity here at 3. This function, because I made its integral equal to 1, is an example of something called a probability density function. Probability density function. When the function is always greater than or equal to 0 and integrates to 1 over whatever interval it's positive over, then it's called a probability density function, or PDF. And any PDF, in theory at least, can be used to model a data set from statistics. What do I mean by model a data set? I'll get to that. It doesn't mean it's a good model for the given situation, but in theory, it might be a good model. You have to test it against the data to see if it's a good model. Mathematicians, statisticians, scientists, engineers, actuarial scientists, they all use probability density functions if they're doing advanced applications of calculus all the time. Now, they may not always be thinking about the calculus, but it's always in the background. probability density function, or PDF. It can be used to calculate probabilities. How? By integrating. Like you could ask, what is the probability, which I'll write as PR. Sometimes I just write it as a plain P. PR for probability that a randomly chosen member of my data set is between 1 and 2, say. Pretending that this function is a good model for my data set, what is the probability that a randomly chosen number from my data set is between 1 and 2? I could represent that symbolically like this. You find this probability by integrating this PDF. But wait a minute, what is this PDF thing? I mean, how is it modeling the data? Let me give you just a little bit of intuition. This is modeling the data in such a way that where the graph is higher, the data are denser. That's why it's called a probability density function, or just sometimes it's just called a density function for short, a DF instead of a PDF. The data are denser where the graph is higher and less dense where the graph is lower. This is modeling a situation where your data is clustering close to 3 without going over 3. Most of the data is near 3, very little is near 0. And between 1 and 2, there's an intermediate amount of data. Now you got to use your imagination. I don't actually have data here. You need to imagine, you need to pretend there's some data set this is modeling out there for some application. And ideally, it's a lot of data, maybe thousands of data points, instead of just like 15 or something that you're using this to model. So to find the probability that X is between 1 and 2, what should we expect for the answer? Relatively big, relatively small, or moderate? Well, 1 and 2 is again where the data are sort of intermediate in their density. It's certainly not going to be a relatively large number. Might be moderately big. How big? I'm going to guess 0.1, 0.2, 0.3, something like that is what I'm going to guess. How do you find it? You use the PDF, you integrate it from 1 to 2. So in this case, you're integrating 1/9 x squared from 1 to 2. That gives 1/27 x cubed from 1 to 2. Using the fundamental theorem of calculus, that's 1/27 times 2 cubed minus 1 cubed. 2 cubed is 8, 1 cubed is 1. So this is 7/27, which is, it's going to be 0.2 something, I think. 7/27, about 0.26. If this PDF is a good model for your data in a given experimental situation, you would expect about a probability of 26% of a randomly chosen data point being between 1 and 2. 26% chance. Probability is always forward-looking. I'm about to randomly select one of my data points. I'm wondering, what are the chances? What are the odds that it's going to be between 1 and 2? I don't know yet until I actually observe that data point, whether it is. I got about a 1 in 4 chance that it will be. On the other hand, if I had tried to find the probability of being between 0 and 1, I'd do the same thing, except the integral would be from 0 to 1 instead of 1 to 2. I'd get 1 cubed minus 0 cubed over 27. 1/27, that's a very small probability. Only about a 4% chance that a randomly chosen data point is between 0 and 1. The rest of the probability is the chance that it's between 2 and 3. That's going to be relatively high. The total probability's got to be 1. That represents 100% of the data. 1/27 plus 7/27 is 8/27. 1 minus that has got to be the chances that's between 2 and 3. About 70% chance that a randomly chosen data point's between 2 and 3. So that's an application of integrals. We can continue applying integrals to this idea. It's also often useful when you've got a PDF, a probability density function, to also create what's called a CDF, a cumulative distribution function, where you effectively are adding up values of the PDF, meaning you're integrating it. And it ends up being an antiderivative of the PDF. You call it capital F of X. It's the integral of the PDF from the lowest possible value where the PDF is non-zero to an arbitrary variable upper limit, X. We've talked about this last week, allowing the upper limit of an integral to be a variable. It's way more useful than you would imagine. In fact, here's how mathematicians mostly think about integrals. They don't think about integrals necessarily as wanting to always find particular areas. They think about, yes, they know about how integrals are related to areas, but they think about it more in terms of using the areas to define functions. That's what we're doing right now. That's how most mathematicians think about integrals. Do scientists and engineers think that way? Sometimes, just not as often as mathematicians. Scientists and engineers are usually thinking about getting numerical answers for questions. They're not thinking about generalizing. The mathematician is thinking about generalizing what they're doing. Effectively evaluating infinitely many integrals at once is what we're doing here. I can do this integral for any value of X. It really defines a function of X. But what do I call the variable for little f? Well, pick anything you want except X. Although I will tell you in science and engineering classes, sometimes they get sloppy and they put an X there anyway. That technically is bad because it's confusing. I mean, not that this is a ton clearer, but it is a little more clear because we're emphasizing that the true variable is the upper limit of the integral. Use another letter like T or U or whatever you want. Is T time? Not necessarily. So I'm integrating same function, except I'm using a T here, 1/9 T squared from 0 to X. That's going to give me 1/27 T cubed from 0 to X, which as long as X is bigger than 0 and smaller than 3, that's where this is valid. I can say the answer is 1/27 times X cubed minus 0 cubed, or X cubed over 27 if X is between 0 and 3. I'm really doing this calculation assuming that's true. X is between 0 and 3. What about if X is not between 0 and 3? What if X is less than 0? Then I'm really integrating from 0 to X where X is negative here, and that would be that's no area there, right? That graph is on the horizontal axis. It doesn't have any area under it or above it. The answer has got to be 0 when X is negative. And when X is bigger than 3, I'm really integrating from 0 to, say, a number bigger than 3. I'm just calculating the area under that curve, which we already know is 1. That's how this curve was created in the first place, to make the area under it equal to 1. So f of X is ultimately a piecewise function. You can say capital F of X is 0 if X is less than 0, 1/27 X cubed if X is between 0 and 3, and 1 if X is bigger than 3. This is actually a continuous function, and its graph looks about like this. Here's 3, here's 1. That's what the graph of capital F looks like. In between 0 and 3, it looks like a cubic, 1/27 X cubed. When you've got the CDF, the cumulative distribution function, you can use this to find probabilities as well. The same probability, PR, that X is between 0, 1, and 2, can now be found by doing capital F of 2 minus capital F of 1. Because that's the same as doing the integral that we already did. Because capital F is an antiderivative. We're talking about the fundamental theorem of calculus here. So this is 1/27 times 2 cubed minus 1/27 times 1 cubed. In the end, it's the same answer, 7/27, about 0.26. Let me illustrate these ideas with some of Mathematica's simulation capabilities. Then I'm going to hint at a more important example of a PDF. And then we'll start reviewing for the exam. So, and again, this mathematic I'm going to show you is something I wouldn't necessarily, test you on. I'm not going to test you on this. It's just something I want to share with you. Let me go ahead and type this function in. I could type it in as a piecewise function, but I don't have to. X squared over 9, that's my PDF. By the way, I mentioned this, but I forgot to emphasize it. This is again called a CDF. Stands for cumulative distribution function. Cumulative distribution function. There are discrete versions of these things, by the way, that come up in discrete math and are also used in probability and statistics, where you're not differentiating and integrating, you are essentially just plugging numbers in and doing additions and subtractions. Let's confirm that if I integrate this function from 0 to 3, I do get 1. It is a valid PDF. I'm a semi-expert in Mathematica, but I have to look things up too. I forget syntax. The way I do things is I go to the help menu documentation center, and sometimes I have to search for things from scratch. Sometimes I remember the name of the command, but I just forget how to use it. The command I'm thinking of here is called probability distribution with a capital P and a capital D. That's what I just typed in there. And yes, there's kind of general information about it up here, but it's more useful typically to do examples. So I'm just going to copy and paste this code over here and then modify it evidently. Evidently, I need to change this to my function that I'm using here, f of x. And evidently, this is the interval in which it's defined. I need to change that to 0 to 3. What's happening when I use this? Well, it doesn't seem like much happened. I just entered it. But something did happen. Mathematica did some calculations and stored the results of those calculations. I'm not showing you what they are in this variable that, well, it looks like a cursive D. Isn't that pretty? Cursive D is the variable in which Mathematica stored results of some calculations. How do I access those results? Well, you got to know what can be accessed. One thing that can be accessed is the average or mean of those results. What is the average of the data that this is modeling? I haven't told you how to find an average for a PDF, but there's the answer, 9/4. Do notice that that is closer to 3 than it is to 0. It's 2.25. Remember, the data are clustered close to 3. Not so clustered close to 0. You should expect an average close to 3. It's 2.25. Is that literally like taking a bunch of numbers, adding them up, and dividing how many there are? No, it's not. It's a more theoretical kind of average. That's an example, one thing we can do. Something else we can do that's maybe more significant here is we can simulate it. There's a command called random variate that will take this distribution and simulate taking values from it. So if I enter this, I should get a number most likely relatively close to 3, closer to 3 than to 0. I did. Do it again. Probably a similar kind of thing happens. Well, that's closer to 0 than it is to 3. Most of the time, it's bigger than 1.5. I just keep re-entering it. Can I do a bunch of data points all at once without re-entering it all the time? Sure, put a comma, say 100 here to get 100 data points. There's 100 simulated data points, most of which are closer to 3 than they are to 0. Look over this list. Most of those numbers are closer to 3 than they are to 0. I can average those numbers themselves. I can store this in a variable I can call data. Every time you enter it, you get a different data set. if I calculate the mean of those data values, this is adding them up and dividing by 100. It's not exactly 2.25, but it's not too far away. That's like if you've had some stats, that's like a sample mean. This is more like a population mean, mu, if you've had stats. This is more like a sample mean, X bar. If you haven't had stats, it's okay if you don't know what I'm talking about. Right? And I don't have to stop at 100 data points. I could do 10,000, for example, very quickly, in fact. There's 10,000 data points, simulated data, and I can compute the mean. That should be very close to 2.25, and I don't want to see all those numbers. If I put a semicolon, it'll suppress the output. This should be very close to 2.25. It is 2.24. I can make a histogram of the data, which is essentially a bar chart showing me what percentage of the data are in various different intervals. There it is. For example, out of 10,000 data points, this highest bar is close to 3. It goes from 2.9 to 3. Its height is close to 900. About 900 data points are between 2.9 and 3, is what this is saying. About 9% of the data. Between 1 and 2, it should be about 27% of the data based on the calculation we did with the integral. If I added up all the heights of these and divided by 10,000, it should be close to 27%. Will I do so? I won't take the time to do so. Notice that this graph kind of looks like an x squared graph. It is. It's essentially very similar to the graph of the PDF in its pattern. A more important example of all this comes up with something called the normal distribution. The normal distribution is the most famous PDF out there. What is its formula? I can get Mathematica to show it to me. PDF, normal distribution. Mean mu, standard deviation sigma as a function of x, there is its formula. The most common thing to use is a mean of 0 and a standard deviation of 1. And the formula simplifies a bit. That's the PDF for the most famous probability distribution out there that's used in statistics all the time. Bell-shaped curve. It's the basis of grading on a curve. Grading on a curve is a good thing if your professor's exams are really hard. Certain percentage of people get an A, certain percentage get a B, C, D, and F. Everything in the past, like 50 years ago, was always graded on a curve. My dad was always graded on a curve. It's bad if the test's too easy. My dad had a college class in the 60s where the test was too easy, but the professor still graded on a curve. Everybody got above 90%, but still a certain number of people failed. It was like 98 was an A, 96 was a B, 94 was a C, 92 was a D, and 90 or 91 was failing. And my dad got 91 or something like that. So he did well on the exam because it was graded on a curve, though he failed. Because that was what they did. A certain percentage of people get all those grades. That's the way they used to do things. That's actually a good thing if the test's really hard, because then you might pass even if you get 10%. You might get an A even if you got 20%. In fact, there was a class I took even where I got an A even though I got like 35%. It was a really hard physics test at Bethel mechanics class. I didn't know that I got an A. I got 35%. I'm like, oh, I did terrible. Professor didn't tell me it was one of the high scores on the test. And I didn't ask anybody. So I ended up and did that kind of thing the whole entire semester. I'd get my grade back in the mail those days. It was like A. I was expecting it like a D. It was an A. What? Okay. What is the CDF in this case? You integrate the PDF, but what is it? It's 1/2 ERFC of negative x over square root 2. What in the world is ERFC or ERFC? It's just a function you've never heard of before. It's called the complementary error function. Normal curves are used a lot in science. from measurement errors, modeling measurement errors in experiments. And they call it an error function because of that. The C stands for complementary. I won't go into details. Okay, I'm not going to test you on this. I'm just trying to expand your mind about possible applications. You may forget about this tomorrow, but maybe a few brain cells in your brain will remember it. And then when you see it in a class a year or two from now, you're like, oh, okay, I kind of remember that a little bit. It's related to calculus, at least. Related to derivatives and antiderivatives, to integrals. To get from here to here, you essentially do an integral, but not in a way that you're used to. You're using the integral to define a function. To actually compute these values, you actually have to do numerical integration, like a left-hand sum and a right-hand sum and average sum to get a trapezoid sum. Actually, there are better methods called, ultimately, Simpson's rule is the best numerical integration method for approximating integrals. And you have to do that kind of thing. You have to approximate them because you just don't have built-in calculator functions to do these things. Integrals are the ways new kinds of functions are created. Here's another quick example. What's an antiderivative of cosine of x squared dx? Fresnel C. Okay. It's a function you've never heard of before, but evidently named after somebody whose last name was Fresnel. The C stands for cosine, Fresnel cosine. If I change the cosine to sine, it becomes Fresnel S. Fresnel S. Does that have applications? It must. Otherwise, they wouldn't bother naming it. I think some applications of this occur in, for example, optics. These Fresnel functions are useful in optics.